Okay, so let's get started again for today. We ended last time talking about, we were in the carboxylic acid derivatives chapter, and we had started talking about reactions of esters. And I think the last thing I had on the board was hydrolysis of esters, which is also called saponification. And, you know, I know all of you have taken biology. That's probably a term you talked about in biology and in reference to fatty acids. But saponification is basically hydrolyzing an ester, which gives the carboxylic acid as the product. And last time we ended the lecture talking about that, and remember I was emphasizing the fact that in these reactions with the transformation, what's in the box for the carboxylic acid derivative is just replaced with what the nucleophile is. So the saponification is just a simple transformation of ester to acid. And the mechanism is the same as what we've been seeing for all of these carboxylic acid derivatives, so that we can move forward then from that and talk about what happens if we use a different nucleophile. This is what happens with hydrolysis, where basically water was my nucleophile and it was under basic conditions, so the nucleophile was actually OH minus. Well, what would happen if you did an aminolysis? And that's going to be where you're using, what is the nucleophile? You're going to be using an amine. Okay, and so based on what we know in all the previous reactions, if we have an ester, specific example here, and this is of course be what your flashcard would look like. Here I'm going to take my ester and I'm going to react it with an amide. And let's just use a simple example of ammonia, the simplest amine we can come up with. What's going to happen in the transformation? It's going to be a nucleophilic acyl substitution. So what's in the box, which is this OR leaving group for the ester, is going to be replaced with the nucleophile. So the transformation is simply producing an amide. So again, ester being transformed into amide. Okay. Now this reaction is not used that frequently as a way to make amides. You can do this synthetically. It is a workable transformation, but the much better reaction is when you had the acid chloride and reacted it with the amine. So this is like a secondary reaction synthetically. If you were trying to make an amide, the more appropriate method would be to use the acid chloride, remembering the two equivalents of amine to get the amide. But this reaction will occur. And then a review, the next nucleophile we can use when reacting with esters is using hydride. So it's doing a reduction. Okay, and that's where H minus the hydride is the nucleophile. And we've talked about this before, and so just an example that I think we used even on the material for the last test. If you have an ester, you can treat it with a hydride reagent, and for the ester, remember it has to be lithium aluminum hydride. We have the aqueous acid workup, and the result of that is, hydride is going to be the nucleophile reacting with that electrophilic center of the carbonyl, doing the nucleophilic acyl substitution. So what's in the box, okay, gets replaced with the nucleophile, which is H minus. But remember, in the case of the esters, you're going to have two equivalents because you initially form the aldehyde. Aldehyde gets reduced again to the alcohol. This is all review, so you already have it in your notes. And so the result of this for the product, you would do, again, nothing happens to the double bond. That's review. We did this exact question several lectures ago. We reduce all the way to that alcohol. All right, and in the process, you're also technically, whatever your OR group is in the ester, you're getting that alcohol also. Okay, so that's review. And so two equivalents of hydride, I mean, that was one of the things we talked about over and over again when you had acid chlorides or esters. Remember, any carboxylic acid derivative, when you do a hydride reduction, two equivalents of hydride add. Okay, wouldn't it be nice if there were a way of stopping this after one equivalent of hydride added. We've seen that, an example of that with acid chlorides and other things also. Okay, and so basically we do it like we did before. We have to change the reducing agent to something that is not as reactive, and in this case because of sterics. Do you remember what we used? It's called Dibol. And it is in fact an aluminum hydride, just like LaH, but remember it has that huge, we called them antlers, huge steric groups attached to the aluminum, and so therefore only one equivalent of hydride adds, and you're then able to stop this after one equivalent of hydride has added. So here you're just doing the one nucleophilic acyl substitution where what's in the box gets replaced with the nucleophile, which is the hydride, and you actually stop at the aldehyde. Okay? Dibol is the reagent that will do that. Partial reductions are really important. There's some really important reactions that have been developed in recent history that are partial reductions like this. Okay, and we'll talk about more of those later. Okay, now one thing you have to be aware of with esters is there are cyclic esters. They're still esters. I'm going to draw this particular one, and it's a cyclic ester, and we actually call these, there's a name for them, they're called lactones, and that's kind of an archaic name, but you still hear it used occasionally. So if you ever hear the term lactone, it's a cyclic ester. And so something that I just want to show this example, it's the same reaction we've talked about, but if you have a cyclic ester, you have to remember when you react this with LaH and an aqueous acid, so you're doing your hydride where you do first the substitution and then the addition that gives reduction to the alcohol. What's going to happen to the lactone ring? Because remember, your first equivalent of hydride is going to react here, and then this is going to be your leaving group. So you actually break open the ring because this OR portion of the lactone is the leaving group on the carbonyl. And so therefore you would form this product, where this oxygen here, we'll call him Fred. Fred was the leaving group when you did the initial substitution. So this is Fred over here. Okay, and then this is George, and George ends up here, right, because two equivalents of hydride added to that carbonyl compound. So use this as an example to make sure if you actually see a cyclic ester, a lactone, that you know when you do the initial substitution, the ring's going to open up. Okay, and we'll see this again in a second. Next nucleophile, so we can use hydrides to get reductions, but remember, this is review also. We can use Grignards. Grignards are carbon nucleophiles, so we can use those nucleophiles to react with esters. And so a simple example that you may want to use for your flashcard, you have this ester, and I'm going to react it with a Grignard. Let's just use a methyl Grignard. Remember, we always follow that up with the acid workup. And remember, this is a carboxylic acid derivative, so just like with the hydride, this is review. We've already been tested on this. The Grignard, there are going to be two equivalents that actually add. I don't have to indicate that there are two equivalents, because if I write nothing, then it's assumed that I have enough to complete the reaction, because remember, the first equivalent of Grignard does the substitution, which gives the ketone, and then the second equivalent of Grignard reacts with that ketone to give the alcohol. And so I always get what? Tertiary alcohols. And so that means the product of this would be where I'm adding 2 equivalents of the methyl from the Grignard, and then I have my OH from what used to be the carbonyl. Okay? Now, in the same way we saw before, and just to make sure that we understand this, if you had a lactone, so you had a cyclic ester, when I reacted it with the Grignard, and let's use the same one. Remember, 2 equivalents are actually going to react. We have the aqueous acid workup. So the first one, the methyl is going to add as a nucleophile and do the substitution. So that's going to open up the ring because this is your leaving group. And then the ketone that forms another equivalent of methyl adds, and so you end up, again, always with a tertiary alcohol. So here's what used to be the carbonyl carbon. So I'm going to put a little box on that. That's this one right here because 2 equivalents of Grignard have added to it. And then I have 1, 2, 3, 4. So 1, 2, 3, 4, 5 total. 1, 2, 3, 4, 5. And then this is the OH that's formed from this leaving group once it gets protonated with the acid. Okay? So hopefully what you're seeing as we go through these is these reactions, or the transformations, are easy. These are review. We've talked about them already. And so even though it looks like we're doing a lot of reactions, it's really all review. Okay? So now we want to transition from esters into amides. So another functionality. And so amides, again, another carboxylic acid derivative functionality. So we want to talk about how you prepare them and what reactions they undergo. But again, this is all redundant because we've already talked about, reactions that give amides. We just, 3 minutes ago talked about that. So these reactions are all things that you've seen. We're in this redundancy circular thing where we're talking about the same reactions over and over again, either preparation or reactions of. Okay? And so just to give you an example of what I'm talking about, when we talk about the preparation of amides, remember a minute ago in this lecture I said the best way of forming an amide is not by reacting an ester with an amine, but by going back and reacting it with an acid chloride. So we talked about this in reactions of acid chlorides. Now we're talking about it in preparation of amides. And that's basically that you can take an acid chloride and react it with something like ammonia or a primary amide or a secondary amide. You can also use tertiary, but not as well. And then basically you're going to form the nucleophilic acyl substitution product. What's in the box gets replaced with whatever the nucleophile is. And so in this case, I'm forming the amide. Okay? And then here, I'm going to form the primary amide. Here, I'm going to form the secondary amide. And I'm going to put primes there. So basically, this is the best way of making amides. But what was the catch? Do you remember? When we did this, we were producing HCl. And so when you're doing this, you're having to use 2 equivalents of the amine in order to handle the HCl that's formed in the reaction. All right? And so this is the best way of preparing amides, acid chloride and amines. Okay, what are the reactions of amides? Okay. Well, they'll undergo pretty much the same reactions we've seen with, the other different functionalities. So for example, the first thing we'll talk about is hydrolysis. And that is what happens if I take an amide. Let's just use a generic, amide with no R groups attached. And let's react this with water. Okay? And in this case, there are two different ways of doing the hydrolysis. We can think about it occurring under acidic conditions or under basic conditions. Okay? And so we're going to start looking at it from acidic conditions. And we're getting to the point now where we're only about 45 minutes left in content for Organic Chemistry 2. This is the second to the last lecture. Okay, so we're almost done with the course. So I'm assuming now that y'all are pretty good at organic chemistry. If you have, any carbonyl compound in the presence of an acid, we know what happens, right? The carbonyl gets protonated. That makes your carbonyl carbon more electrophilic. We've been over that a million times. And so that means that you'll transform that amide into this protonated form. And that basically makes this more nucleophilic towards the addition of water. So water adds as the neutral nucleophile, reacts with the electrophilic center of the carbonyl, right? Breaking the pi bond, moving the electrons out to that O. And that's going to give me tetrahedral intermediate. The carbonyl oxygen was already protonated, right? I've added this neutral water as my nucleophile, and then I have this NH2 that was present from the amide, okay? And so what do you think happens now? Our good friend proton transfer. Okay, this nitrogen that's conveniently sitting here, and again, is this proton transfer intramolecular or intermolecular? It doesn't really matter. But you just envision that nitrogen can pull off a proton, and when it does, it moves the electrons to this oxygen. And so I'm going to end up with this intermediate now where I've protonated the nitrogen. R group is still there, it hasn't changed. And now I've pulled the proton off of what was the nucleophilic water that added, and I end up with this product. Okay? Or I should say intermediate. And then what's going to happen? Well, I've got to figure out a way to get towards product, because what's going to happen? If this is what's in the box, it's going to be replaced with whatever the nucleophile is. And the nucleophile here is water. So that means my final product is the what? Carboxylic acid. When you hydrolyze an acid derivative, you're going to get back the carboxylic acid. Okay? And so in order for this to happen, you have to envision, it doesn't matter which OH you move this from, but you move these electrons back in from the OH bond, reforming the carbonyl, because when you do, you lose that NH3 group as a leaving group. And it's a good leaving group because it has a positive charge. Your induction is, you're pulling electrons towards that nitrogen. It wants to pull the electrons from the bond. Good leaving group. The result of that then is you have reformed the carbonyl. You have the OH, plus you formed this, I'm sorry, when you first move it in, it's still got a positive charge. You form this NH3 group as a leaving group, okay? But your electrons have moved in, and the easiest way of showing this, I should just say, let's just show it like that. All right. Now, what would happen if you did the same hydrolysis? but I'm going to do it under basic conditions, which is basically going to mean that my nucleophile is now OH minus instead of neutral water. So how would we do the mechanism for this? Now, the unfortunate thing is if we were all in class together, usually at this point, I divide the class in half and have you all figure out the acidic and the basic mechanism for this. But since we're recording, I have to do it all. But basically now, in general, when you have something that's base catalyzed, so this is a hydrolysis, I'm under basic conditions. So now, remember, it's got nothing to do with protonating the carbonyl. That's what happens in an acid. But here I have a base, so basically that means that my nucleophile is more nucleophilic because instead of being neutral water, it's OH minus. So that acts as a nucleophile, reacts with the electrophilic center of the carbonyl, breaks the pi bond, moves the electrons out to the carbonyl oxygen, forming the tetrahedral intermediate. So I've moved the electrons out to my carbonyl oxygen. I still have my NH2 here, and I have my OH that's added as a neutral nucleophile. Now, you simply move these electrons back in to reform the carbonyl, and when I do, I lose NH2 as my leaving group. And so that means that I would form that as my product. Okay? And now, because it's under basic conditions, one thing you could show is under basic conditions, your product's actually going to exist as that, because your carboxylate is going to be what's present under basic conditions. But it's okay if you were to show this as the product. All right, and so hydrolysis using water as a nucleophile is a reaction that amides will undergo. And I'll repeat again, anytime you hydrolyze a carboxylic acid derivative, you will get a carboxylic acid. Okay? Now what about reductions? Reduction of amides. Okay? Reductions of amides are a little bit different than other carboxylic acid derivatives. So we're going to spend a minute talking about that. So if you're doing a reduction, that means the nucleophile we're going to use in the standard sense is, our reducing agents are basically hydride reagents, where H minus is the nucleophile. All right? But when you reduce an amide, unlike the other cases, your product is not an alcohol. It's actually an amine. Okay? And so basically with my other cases, you would see, your carbonyl gets reduced to an alcohol. That's kind of the normal thing that happens with carboxylic acid derivatives or aldehydes and ketones. You react it with a hydride reagent, you're basically taking your carbonyl and converting it into an alcohol. It's not what happens with amides. With an amide, your carbonyl ends up being a CH2. Okay? And so therefore the overall transformation, you end up with an amine. So let's look at an example of this. And this could be something that you put on your flashcard as your example of this reaction. So here I have my amide, and let's use this methyl amide. And I'm going to react it with a reducing agent. Sodium borohydride, remember, does not work on carboxylic acid derivatives, so LAH is what I'm going to use. And always following that with acid workup. So there's nothing different about the conditions for this reduction, but the difference is now is when I reduce this carbonyl becomes a CH2, and I've reduced that to the amine. Okay? So different result. Well, if there's a different result, there must be a way of explaining it. And what would explain the difference in this reduction? You're right, it would be the mechanism. So let's look at the mechanism of this. I'm going to change markers here because this one's getting kind of low. All right, so we're going to start with just a generic amide. And since I'm doing a reduction, we know the nucleophile is simply this hydride. And knowing what we do, what's going to happen, right, is this is going to react with the electrophilic carbon of the carbonyl, breaking the pi bond, moving electrons out to O, forming the tetrahedral intermediate. That's always what happens in these reactions. So I put my brackets there, and I'm going to draw my tetrahedral. And so that's NH2. So that's the NH2 group. I've added an H. Let's make this the wedge. I've added an H as my nucleophile, and I have that O minus. Now, based on my experience, the best way of showing this is, I mean, you can show it as the O minus, but there's the aluminum from the reagent, LAH, that's sitting out here with a plus charge. And so it's the counter ion to this. And this is just for this is free information. It's not going to be tested. Just so you know, it looks like, you know, it would be an ionic interaction, so you usually don't even show these with the tetrahedral intermediates. But the reason I'm showing it is in work that I've done, you know, independent research, this is actually more of a covalent bond than an ionic. And so just to let you know that sometimes you'll see that drawn where there's actually a bond between those two, same as this bond, instead of it being ionic. But let's just pretend it's ionic. All right, so you form that tetrahedral intermediate, and then what's going to happen? Well, it's hard to tell. But remember what I just said about this being more of a covalent bond. If it helps, think about it this way, because what actually happens is the electrons from this nitrogen come in, okay, to form this pi bond. And so what you're thinking of is this is starting to resemble what happened when we had amines reacting with ketones and aldehydes. Remember, there's a different mechanism. So it's kind of starting to look like that, right? That amine formation, remember? Because what happens is you kick this off as the aluminum oxide, all right? And so when that happens, you actually form this. Since these electrons moved in, and this, I'm sorry, this is a nitrogen. Since these electrons moved in, you know, you end up with a positive charge on this nitrogen, okay? And so this is, in fact, you know, looks a lot like amine formation, right? And you've also, by the way, have that as your, now as your leaving group in the counter ion. Okay, and then what happens is, remember, you have your second equivalent of hydride. Because when you have carboxylic acid derivatives reacting with hydrides, they react with two equivalents. So this is kind of the result of the addition, where you have something that looks like an amine, but now a second equivalent of hydride reacts at this electrophilic center, which pushes these electrons out to the nitrogen. So this is almost acting like a protonated carbonyl. And when it does that, I've now added 2 hydrogens, right? And I have my NH2. So you can see what happens is I formed an amine here after the second equivalent. And therefore, it gives a different result than we saw for the other carboxylic acid derivatives. Now, let's see how much time we have. We're not going to go the whole time on this lecture. So I'm wanting to kind of spread out the material that's left. And so one result of this different mechanism is we get a different result if we have something like this. Let me just put, for fun, put a couple methyl groups here, it doesn't matter. If I have this compound, remember a minute ago when we talked about esters and we talked about their reduction and you have 2 equivalents of hydride adding, you actually opened up the ester if it was cyclic. Remember we called it a lactone and said the lactone ring opened. Well, if we have the corresponding cyclic amide, because of the different mechanism, we have a different result. You would expect that, right? Because we said that you don't have the carbonyl reducing to an alcohol. Now you have this becoming a methylene, a CH2. And so these cyclic amides, which are called lactams, so they have an archaic name too, a lactam. If you have a lactam and you react it with something like LAH, followed by an aqueous acid workup, you do the reduction you would expect. As notice in that mechanism, the nitrogen is not a leaving group. It doesn't leave. The carbonyl leaves. Okay? And so it becomes a CH2. And so the ring never opens up. Now you just have a cyclic amine. So be aware of that. The mechanism predicts this. But be aware of that because this does not cleave. Okay? Now, when we talked about esters, we talked about partial reductions. Remember we said if you used LAH, an ester would reduce all the way, right, to the alcohol. And then we said, wouldn't it be nice if you could stop after 1? And we said that you could produce an aldehyde if you use dibol. So that was a partial reduction. Well, it turns out that it's only been in recent history that a transformation was discovered that you can partially reduce amides. It's not easy because it's a different mechanism, remember, than what you saw with esters. And so if you have an amide like this, you can in fact react it with dibol, followed by this zirconium hydrochloride, which is called Schwartz reagent. And Schwartz reagent has been around for a long time. It's a cyclopyridinium zirconium hydrogen chloride. It's a, you know, an organometallic reagent. Okay, you use these 2 things together, 1 equivalent of dibol and 1 equivalent of Schwartz's reagent, and you do a partial reduction. Now I'm going to pause dramatically for a second because, you know, I can't actually look at you in the face when I'm asking this question, but based on the mechanism we just saw for the reduction of an amide, remember we saw 2 equivalents of hydride adding and we ended up with the amine. But what was the result after 1 equivalent of hydride added? So what would be the partial reduction product. Remember, it looked like imine formation. It was the imine. And so that means if you partially reduce an amide, you actually end up with an imine. Okay? And this reaction, this partial reduction of an amide to an imine, is kind of an interesting reaction. And I think that in lab, some of you told me that you heard the story about how this particular reaction, which won an American Chemical Society award for innovation, it's actually used in the commercial production of Taxol, which is a ovarian cancer drug. Was used for breast cancer for a time. It has some other uses, but I think it's mainly ovarian cancer now. But this partial reduction played a role in that commercial development of Taxol, and it's a reaction that was discovered, in the early 90s using Schwartz's reagent. All right, and so at the point we are now, we're done with amides, and so the only functionality that's really left for us to talk about are nitriles. And we're going to save nitriles for the lecture on Friday. So today is actually Wednesday, virtually, and there'll be a lecture on Friday, and it's basically just going to be what I hope to do is finish up nitriles, which are the carboxylic acid derivative reactions. So it's going to be very similar to what we just saw with amides. But then I'll probably spend a little bit of time talking about the reactions that are carbonyl condensations and alpha substitution reactions. Remember when we started what seems like a century ago with carbonyls, and we had the nucleophilic acyl addition, nucleophilic acyl substitution, and then we had the carbonyl condensation and the alpha substitution. We'll talk a little bit about those last two, but just a very brief review just so you know. But it's very similar to the reactions that we've been talking about. It's not a big difference. But I also will want to spend a little bit of time doing some synthesis problems. And I'd like to give you one now, if it's okay. I'm going to be doing these in the actual synchronous sessions at 11. Today, which is Wednesday, there'll be one. We're going to do it on one Monday. And then on Friday, too, I'll come in and try to give a couple of synthesis problems at the beginning of those sessions, just for your practice. And I did put some up on a Moodle. But let's see if we can work this one. Okay, I thought I could save this marker, but it's good we only have one lecture left. All right, how would you go about doing this synthesis? And I'm going to give you a minute to look at it, and then we'll work it together. I know you can probably hit pause if you still want to work some more on it, but let's start to look at it. As we've been talking about in the 11 o'clock sessions, those 3 or 4 of you that have been able to come. We're getting to the point in synthesis where it's not only important to count the number of carbons, but it's also starting to be important to try to recognize what carbons in your proposed product, where they are located in your starting material. So you have to really kind of spend some time before you start your retrosynthetic analysis kind of analyzing these. Because what I'm looking at here is I know that there's really only one reaction that I can do on a cyclic ether, and that's to cleave it open with either HI or HBr. So I know that that's how this has got to start because I'm going to an acyclic system. So if there's 1, 2, 3, 4 carbons that are going to be present when I open it up. And if I used HI, so I'm looking at, because I have this I here, so that would make sense, right? That would mean that this carbon right here would be one of these 2 carbons, whichever one, was that the I reacted with. And that would mean that this oxygen would be, have to be somewhere else when you opened it. And so that means that this carbon here would have had to have an OH on it at some point. Okay? Because these are the 4 carbons, I'm guessing, that are from this starting material. Okay? So now I just start doing my retrosynthetic analysis. I've kind of figured out where the I came from. So I can just let it go along for the ride, because it's going to be formed in the first forward reaction. Okay? So now I'm looking at the different functionalities. I have this tertiary alcohol here, and I have this secondary alcohol. Well, anytime I look at a tertiary alcohol like this, I always think that I can very easily retrosynthetically go back to where that's a carbonyl. Because I know that reacting that with a Grignard reagent would actually give me product. Okay? And so that means going back from there, now you have to think, well, do I know of any way of making that a carbonyl? Well, yeah, I could make it from an alcohol by doing an oxidation. And the reason I'm doing this is because then I also know that leads me back to this diol. And we know how to make diols from the corresponding double bond, right? And so I'm very quickly seeing this retrosynthetic flow because of the experience I have with these reactions. Well, this doesn't look anything like I would get as a result of the cleavage, right? But do we know of any way of making double bonds like that? Have the correct number of carbons from when I open this. So I'm going to have to go back to something, and I'm just going to put an X there. It could be, I, Br, Cl, it doesn't matter. But I know that I can eliminate an alkyl halide to get this, just doing an E2 reaction. And then I can go back from this. How could I put a halide in that position? Well, I could do it from the corresponding double bond. And that double bond I know I could get from the cleavage product because I know how to eliminate OHs to get double bonds. And I know that I can form this by cleaving open that ether. Okay? And so forward reaction is just HI gives me this. And then do you remember what the reagent is? POCl3 gives me the alkene. And then let's just use HCl to make this a chlorine. It's going to go to the more substituted side, Markovnikov, right? That's going to give me this. And then I just treat this, and this is where you have to be careful because you're going to get a mixture. If I treat that with one equivalent of base, I'm going to get the major from the elimination of the chlorine is going to be this. But I also get some elimination of the I. And so, it's a mixture, but that's okay with a synthesis as long as you know that. And then how do I get the diol? We can do the hydroxylation. So there are several ways of doing that. Potassium permanganate is one, right? As long as it is basic. So I form this, and then again, I'm going to oxidize, but there'll be a mixture because I have two OHs. Okay, and so I'm going to do, just PCC, knowing that there'll be a mixture, but I'll get some of this. And then now here's the problem. Initially, when I look at that, I'm saying, well, I want to use the Grignard. But what's the issue? I have an OH. Okay, and remember, OHs interfere with the Grignard. So what I'd have to do, I'd have to add the step. And I didn't realize that until I'm going forward. And then I see it. And so that means that I have to kind of divert here. And put the TMS group on. So I protect that, right? Then I react it with the methyl Grignard. And then remember, when I do the aqueous workup, it takes care of protonating this and removing the protecting group. Okay? So that synthesis is one to look at because it involves, for the first time, the use of a protecting group. But it's also, you need to be practicing these flows because I had to think back to the first semester. For some of these reactions, I had to remember Markovnikov addition of HCl and the E2. Okay, and it's also teaching you that there may be mixtures. When you're doing certain reactions, there may be more than one product that forms, and in a synthesis, that's okay. You try to avoid it if possible, but in these cases, it's not possible. You could maybe think about whether there are other ways that you could avoid that, but this synthesis is perfectly okay. All right? All right, so next time, we will talk about nitriles, and we'll talk a little bit about the carbonyl condensations and alpha substitution reactions, and that'll take us through the end of the semester. Okay? Now, if you're listening to this, try to be at the synchronous meetings on Wednesday and Friday because we'll be going over some synthesis live where you can ask me questions, but also I'll talk a little bit about the test. Okay, because the test is on the syllabus for May 11th, which is, this is Wednesday, so it was a week from Monday. And I'm going to give it to you Thursday morning, and it'll be due Monday, basically by midnight, I think is how I'll do it. And then very soon after that, because our final exam is scheduled for a week from the 11th, so the 18th. I will give you the final exam before that and give you a window to complete it, but it must be completed by the end of the day on the 18th, because then I need to grade, because I know that everybody's listening to this video, so I know, Liz, you're graduating, so I need to get your grade in. If there's anybody else in the class that's graduating and you're a senior, I need to make sure that I get your stuff graded first. Okay, so let me know. Liz, you don't have to worry about it because I know about you. All right, so I will see you on Friday.